Hey again, everyone. Another one of my spring break review videos. This one is going to be for chapter 25, Hardy Weinberg. Did I finish this question? We'll find out. Okay. Actually, we explored this question a little bit in a previous review, and that was in week 7, I think. No, it was in week 6. And oh, goodness gracious. Hey, go away. Also, take that survey, please. Too late now, I guess. But actually, no, it's never too late. It was question 6 in this review. And I did not ask it properly. This is the way I wrote this question is actually a common way that people make mistakes when answering Hardy-Weinberg questions. So I wanted to explore it once again, Hardy-Weinberg equilibrium. Let's get started. So for example, going back to Avatar, in the Southern Water Tribe, water bending is coded for by the alleles capital and lowercase w, where the capital dominant can't bend and the recessive lowercase w can bend. Among the non-benders of the Southern Water Tribe, people that are heterozygous at the bending locus have slightly elongated fingers, while homozygous dominant individuals have regular fingers. Of the water tribemen at the South Pole, there are 1,200 waterbenders, 10,800 people with long fingers, and 8,000 non-benders with normal fingers. So let us establish whether or not this population is in Hardy-Weinberg equilibrium. Which color should we use? Let's use blue for water bending. So when we get a question like this, it's best to just write out what we know. So we know the alleles, and we know what combination of them make for the different phenotypes. So let's establish the different genotypes. So non-benders, all right, actually, we know that there are 1,200 water benders. In order to be a water bender, in order to bend, you need the recessive W allele. So water benders, since they're recessive, have to have lowercase w, and are 1,200 in number. People with long fingers are heterozygous at the bending locus, and so they have a capital W, lowercase w, and there are 10,800 of them, and we have the non-benders with normal fingers who have been previously established to be homozygous dominant, and there are 8,000 of them. So we have our proportions of genotypes. This WW, or the combination of WW that an individual has, which determines their phenotype, whether or not they can bend, what kind of fingers they have, is their genotype. This is a genotype, and a genotype. And so from this, we can establish the number of, or the allele frequencies, the frequency that any one capital W exists in this population, and the frequency with which this lowercase w exists in the population. So let's determine the frequency of the capital W allele. So how many alleles are there, or how many W alleles are there in a bending individual? How many capital W's? None. They have lowercase, there are no uppercase. In a heterozygous individual, there are one capital W allele. And in a non-bending, normal-fingered, homozygous dominant individual, they have 1, 2. So the frequency of capital W alleles are, there are 0 capital W alleles in 1,200 individuals, plus 1 capital W allele or nope, I messed that up. There is one capital W allele. Oh, actually, I also messed that one up. So before we do this, let's just establish how many alleles there are overall. That's going to help us a lot. So there are this many individuals, and every individual has two alleles. So all benders have, or among the benders, there exist 1,200 times two alleles, because there are 1,200 benders and they each have two alleles. So 2 times 1,200 is equal to 2,400 overall alleles. Same thing with this. There are two alleles per individual, and there are 10,800 individuals, which become 21,600 individuals. I think I did that right. 10 makes 20, 800 makes 16, right? And same for these. 8,000 becomes 16,000 alleles. So 2,400 plus 2,100, 21,600, excuse me, and 1,000. Oh my God, numbers. So 24 plus 21, 6, that's going to be 22. 24 plus 16, it should be, well, 40,000 actually. God, why did I do that? It makes sense because there are, well, I guess an easier way to do this is to take the number of individuals you have. This plus this is 12,000 plus this is 20,000. So there are 20,000 people in the water tribe and they each have two alleles. So it makes sense that there are 40,000 alleles. I did not have to go through all that trouble. So there are 40,000 overall alleles. We know this. So there are 40,000 overall alleles. So let's get back to drawing. In the homozygous recessive individuals, there are 0 dominant alleles. That makes sense, right? So there are 0 times 1,200 plus 1 times 10,800 plus 2, because there are 2 capital W alleles, times 8,000 individuals. So there are no capital W alleles in these individuals. There's one in this type of individual, an individual with this genotype, I should say. And there are 2 capital W alleles for the capital W genotype. So this is the number of alleles divided by, or the number of this specific allele, number of this specific allele times, or excuse me, divided by the total number of alleles. And the total number of alleles is 40,000. Let's do that math really fast. So 0 times 1,200 is 0. We have 10,800 plus 16,000 divided by 40,000. 0.31. So allele frequency, actually, I'm going to, the allele frequency of capital W is equal to 0.31. Now we can do some more of this kind of math, or we can take the shortcut, and we know that the total number of alleles, or the total frequency of alleles in a population is equal to 1.0. And this makes sense because 1.0 is saying that 1 divided by 1 individuals have alleles. Obviously, that makes sense. 1 divided by 1 is equal to 1.0. And this just expresses at 100%, the total for any population. And so the total number of alleles in a population is equal to the number of one kind of allele, or the frequency of one kind of allele, plus the frequency of another kind of allele. And we know this frequency, so we can substitute it. 1, or 100% of alleles in the population, is equal to the frequency of this kind of allele plus the frequency of this kind of allele. Actually, no. I hopefully will have the sense to cut this out of the video. Let's pretend I didn't say that and go on to the lowercase allele. And so we have, for the lowercase individuals, there are two recessive alleles in a homozygous recessive individual. So there are two kinds of these allele in this many individuals. There is one kind of recessive allele in this genotype, which is expressed by this number of individuals, 1 times 10,800. And there are no recessive alleles in a homozygous dominant individual. So 0 times 8,000 divided by 40,000. So the number of this specific allele in a population divided by the total number of alleles in the population gives us the frequency of this allele in the population. And that's not 4,000, that should be 40,000. And this works out to be 2,400 plus 10,800, not 800. That is equal to 0.33. Lowercase w is 0.33. So now that we have the allele frequencies that we find in this population, we can determine the frequency of the genotype based on the Hardy-Weinberg equilibrium, obviously. And so let's not clear everything, actually. No, please leave me alone. Actually, we can't do that, never mind. I wish there was a faster way. There's probably a faster way. Okay, so we have that. And so now that we've found the allele frequencies in our population of waterbenders, we can use the Hardy-Weinberg equation to determine if they are in, well, actually, shouldn't speak that way. We can use these allele frequencies that we found within this population, compare it to the equation that would be expressed by a population in Hardy-Weinberg equilibrium. And if they are the same, then we can determine that this population is in Hardy-Weinberg equilibrium. So the equation I'm referring to is that the total number of individuals in a population, 100%, is equal to, oh, wait, I cut that part out. So this 1.0 is like saying 1 divided by 1. 1 divided by 1 is 1. And this is saying I explained it so much better earlier. Oh my God. All of the individuals in a population divided by all of the individuals in a population are equal to the frequency of individuals in a population. So by extension, if this is the total number of, or the total frequency of alleles, all of the alleles in a population is equal to all of the alleles. All the alleles divided by all the alleles is 1. And so all of the alleles in a population are going to be equal to the frequency of all of the different kind of alleles in that population. Oh wait, no, that's not where I was going with this. All of the frequency of all the different kinds of genotypes in a population is going to equal the frequency of all of the different kind of genotypes in the population. So the total number of genotypes divided by the total number of genotypes is 1. So the frequency of the frequency of all genotypes combined, is going to be 100%. And the frequency of a homozygous dominant individual is, in this case, W capital times capital W. And when you multiply these together, it's pretty much like W squared. So you can think of that as W squared, which we know very familiarly, as P squared. So keep that in mind. W squared plus, the same goes for homozygous recessive individuals, it's going to be lowercase w squared. And this comes from the cross. A basic monohybrid cross, if you have a true breeding pair that is homozygous dominant and homozygous recessive, nope. If you have a test cross, you're going to have this ratio of individuals where you have 1 that is homozygous dominant, 2 that are heterozygous, and 1 that is homozygous recessive. So you have 1 to 2 to 1, homozygous dominant, homozygous dominant, homozygous recessive, homozygous recessive, and there are 2 heterozygotes. So 2 capital W, lowercase w. And we know this from our textbooks and lecture slides as P squared. Actually, I'm going to draw it in a different color. We know this as P squared plus 2PQ plus Q squared. And that's what happens if you do P and Q, P and Q. So hopefully that's connecting some dots. Anyway, and we know that this is going to be equal to 1. So we can use some math, and we know the individual values for a single capital W and for a single lowercase w. So we can plug them in. We know that we can rewrite this 1.0 is going to equal capital W squared. So 0.31 squared plus 2 times capital W times lowercase w plus lowercase w squared. And if we do this math, so what we get for this value, this W squared, 0.31 squared is 0.0961 plus 2 capital W lowercase w is equal to 0.2046. And this lowercase w squared is 0.1089, which is equal to 0.1089. 0.4096. So does 1 equal 0.4096? I wouldn't say so, and therefore I would say that a population in Hardy-Weinberg equilibrium would have their genotype frequencies sum up to 100%. But the genotype frequencies of this population, as we see them in their specific proportions that have been defined in the question, do not equal 100%, but only equal 0.4096 or 40.96%. And therefore, because the genotype frequencies that we see in this population do not correspond to what we would expect from a population in Hardy-Weinberg equilibrium, we can say that this population is not in Hardy-Weinberg equilibrium. All right. Yep, Hardy-Weinberg equilibrium, you just have to be able to look at a question, determine what is what allele corresponds to, what thing you're going to plug into what equation. Actually, that's not true. Most of the problem we've been having is determining the allele frequencies. And that can be kind of confusing, because there's like different combinations of alleles, and what the heck? All you have to remember is that you're dividing, if you want to find, for example, the frequency of an allele A, then the frequency of allele A is going to be the number of A's that you see total in a population divided by the total number of alleles, whether or not they're lowercase a or capital A or lowercase b or whatever. And yeah, so you just find the total number of lowercase a's in a population. There's 1 times 1,200, because 1,200 individuals have 1 lowercase a. 10,800 individuals have 2 lowercase a's. So you'd have 2 times 10,800 plus 1 times 1,200. And let's say they were a lowercase b, this would be 0. So yeah, just try to keep everything clear. It's a lot of math, but you can do it, no problem.